Okay. We're going to do equilibrium ice tables. Ice is nice. Don't forget that. Okay, so ice tables. What we're doing is we're finding the initial concentration, the change in concentration, and the equilibrium, or what is that equilibrium, or what is left. Okay, so our first problem, part A, says the equilibrium constant Kp for the reaction below is 1.4, so Kp equals 1.4 times 10, so negative 21st at 25 degrees Celsius. That's just standard temperature. Okay. For the reaction, H2 plus Br yields 2HBr. Okay, part 1 is to write the expression, or the Kp expression. So that will be products over reactants. So you have Kp equals products, which is the 2HBr. You use parentheses here, or brackets. HBr. And since there are 2 moles of this, you put an exponent of 2 up here. That's over the reactants. There's 1 mole of hydrogen and 1 mole of bromine. So H2 and Br2. So that's part A. That's your Kb or Kp expression. Part B, or number 2, whatever you want to say. Okay, you have gaseous H2O and HBr added into a 1.15 liter container kept at 298 degrees Kelvin, which is the same as 25 degrees Celsius. The initial partial pressure of hydrogen gas in the container is 0.782 atm. So, part B, 0.782 atm for hydrogen initially. After we have that, we have, let's see, bromine, we have 0.493 atm. 0.493 atm Br2 initial. Okay, this is the I part of the ice table. This is the initial concentrations. These 2 gases are put into an evacuated cylinder. This means that the HBr at the end of the equation is not yet present. So, when you see this, the question that arises is find partial pressure, write that down, partial pressure of HBr at equilibrium. This means you're going to set up an ice table. Ice table is very simple. What you do first is you rewrite the equation, or the chemical equation, just like that. So H2 plus Br2 yields 2HBr. You have that. Now what you want to do, you're going to make a box. That was a really bad box, but hey, it's a box. Okay, now you divide it into 3 sections for the H2, Br2, and 2HBr, which is your products and reactants. Okay, you start off, you have your I. That's for the initial concentrations, which is for the 0.782 atm of H2 and 0.493 atm of Br2. You have I, then you have C, which is going to be the change in concentration, which is how much of the products goes down and how much the reactants is formed. And then your final part to the ice table is the E. Ice is nice, don't forget. Okay, so you draw your crossbars there. Okay, initially we have 0.782 atms of H2. 0.782 atm. Then you have 0.493 atm of Br2. So you just write that in there, 0.493 ATM. Initially, there is no HBr in the container, so you have 0 ATM. Okay, from here, you look at the number of moles of each of these pieces that are in the container. H2, there's 1 mole, so you're going to lose minus X is what you put here. X is the amount of concentration that goes down. For Br2, or I'm sorry, pressure that goes down. For Br2, there's also only 1 mole, so it's minus X. And for 2 HBr, there are 2 moles in this equation, so it's plus 2X. Okay, so then at equilibrium, you pretty much just take the initial minus the change, and that's what you put in the equilibrium box. So you have for the hydrogen, you have 0.782 minus X. For the bromine, you have 0.4, I'm terrible for, 93 minus X. And for the 2 HBr, you just have 2X. Okay, now we were given in the first part, Kp equals 1.4 times 10 to the negative 21st at 25 degrees Celsius. This is at 25 degrees Celsius, also known as 298 degrees or 298 Kelvin. So what you do is you use your Kp expression and you set this HBr squared. So down here it's 2x squared. I'll write this, or can you turn that for me so maybe see this? You got 2HB. Oops. You're gonna have 2x squared over. You have 0.782 and 0.493 in the bottom, like the Kp expression right here. There's only 1 mole of each, so the exponent is just 1. So you're going to have, okay, it's 0.782 minus x and 0.493 minus x, but the x's are negligible because there's such a small amount of pressure. So you're just going to have 0.782 and 0.493. This is the Kp expression. Kp expression, this right here equals Kp, which is 1.4 times 10 to the negative 21st. We're solving for x, which is the pressure of HBr. So we set this equal to 1.4 times 10 to the negative 21st. And then you solve for x. So you find, let's see, this is going to be x equals square root of 1.4 times 10 to the negative 21st times these two bases down here, which is, or denominator down here, which is 0.782 and 0.493. Close up that parenthesis. And that is all going to be over 4 because 2x squared is 4x squared. Or 2x, all in the brackets, squared is 4x squared. So you're going to divide that by 4. You're going to find x to be about 1.6 times 10 to the negative 11. ATM, because that's the units. Always remember units, it's very important. Okay, now we have x, but 2HBr is 2x, so you have to double that. So quite simply, it is 3.2 times 10 to the negative 11 ATM is the partial pressure of HBr at equilibrium. So you have to calculate Kp for half of the reaction. Let me erase some of this because it's done now. Calculating Kp for a half reaction. So the half reaction of H2 plus Br2 yields 2HBr would be, well, actually this is the reverse reaction. So it will be HBr yields half mole of hydrogen gas plus 1/2 So, we have KP equals 1 over 1.4 times 10 to the negative 21st. I don't even need this, because I'm not doing, this isn't even part of my statement. Yeah, I'm done. What the hell am I doing this? Cut.
You can just edit that out.